Good morning or good afternoon, everyone, and thank you for being here. I'm Simone Serafini, Marketing Specialist for VIS Hydraulics and SmartFluidPower, and I'd like to welcome you to the third session of our webinar series on dynamic simulation. In the first webinar, we saw how to build component models. In the second, we explored how to use those models in system-level simulations. And today we take a step further. We look at what happens when these models don't remain confined to analysis, but are used within company across different departments. So we won't focus only on how to build models or simulate systems, but on a broader aspect, how simulation truly becomes part of the company workflow. More specifically, we show what we have done within the VIS Hydraulics Innovation Center, the R&D Center for Fluid Power co-founded by the Emilia-Romagna region. We look at how model can be used consistently across all phases of a component's life cycle, from the engineering office to the test bench and even all the way to the customer. Presenting today will be Giovanni Cillo, founder and CEO of SmartFluidPower, and Emiliano Natali, engineering coordinator at VIS Hydraulics. Giovanni, over to you and enjoy your the section.
Thank you, Simone. I am Giovanni Cillo, and I am one of the founders and directors of SmartFluidPower. For those who don't know us, SmartFluidPower focuses on lumped parameter dynamic simulation with a specific emphasis on fluid power. SmartFluidPower is an innovative SME founded in 2018 as a spin-off of the University of Modena Reggio Emilia. And this company currently consists of 7 partners, all coming from the fluid power field with backgrounds in academia, research, and also industry. As you can see, our customers all belong to the fluid power sector. We mainly operate in hydraulics, but more generally in pressurized fluid systems, including fuel, water, and similar applications. We focus on virtual simulation. A virtual model reproduces the behavior of a system or a component and helps reduce the number of physical prototypes and experimental tests. In addition to reduce physical prototypes, it allows testing many design configurations directly on the computer without building anything physically. This is useful both in the prototyping phase and in the design activities. It also enables fast optimization of an already developed design, reducing time and costs, and also improving time to market. Our main strengths are based on the use of Modelica language within an open source environment designed for multi-domain systems. This environment is called Open Modelica and promotes co-simulation through model exchange using the FMI standard. We adopt a block-based modeling approach, which is fast and intuitive and based on lumped parameters. SmartFluidPower provides also custom services dedicated to software integration into companies' processes. And as I said, our team is completely specialized in fluid power. So the main tools are Open Modelica, that is an open source environment for dynamic simulation of multi-domain systems that promotes the co-simulation through the FMI standard. And our library, that is written in Modelica code and is specialized for the fluid power sector with a lumped parameter approach. For those who are familiar with simulation, this differs from distributed parameter approach such as CFD or FEM, which may be steady state or fatigue-based. Our approach is based on lumped parameters, meaning that spatial effects are approximated while system dynamics are fully captured over time. We have developed several libraries, an hydraulic library including simplified models of valves, pipes, orifices, cylinders, pumps, and motors, a mechanical library divided into translational and rotational components, a component library that is used for detailed modeling of elements such as poppets, spools, pistons, a signal library containing blocks used to provide inputs and control to the system, and a fluid package that is used mainly to define properties of merely incompressible flow. In addition, we provide development of custom libraries, models, and user interfaces, consulting activities including CFD analysis for models calibration, training, and support. So we work on two fronts. On one side, we develop software tools. On the other, we support companies through consulting activities. But the core of our work is not simply doing simulation. It's about bringing simulation into company processes so that it can become a tool used on a daily basis rather than something separate or occasional. To make all of this concrete, today we won't just talk theory. We'll look at real examples based on the use of simulation within the VIS Innovation Center, with whom we collaborate closely. I now hand things over to Emiliano for a brief introduction to this context.
Yeah, good morning, everyone. Within VIS, we have developed the Innovation Center, as Giovanni said. That is our research and engineering hub created with the goal to support product development and provide our customer with advanced engineering service, including design, prototyping, and testing. Today, we use several simulation technologies as part of this process, such as CFD and FEM and electromagnetic analysis. In recent years, however, the introduction of lumped parameter simulation based on OpenModelica and the SmartFluidPower library has been a real turning point in which we design valves. By building the dynamic models of our valves, we can evaluate their behavior already during the concept and design stage. And this allows to make better informed design decisions, compare alternatives during the early stage, and to reduce also the number of the design variants and number of components. Our goal is not to replace the physical testing, but to complete it. And the simulation helped us to create this strong continuity between the design and the validation of our product, improving our understanding of the right dynamic behavior of the valves, especially under the transient operating condition. And during this webinar, you will see some practical example of how these tools are applied in our daily engineering work.
Okay, thank you, Emiliano. Okay, let's start from a very common situation. In many companies, the engineering office works based on sizing calculations, experience, and design assumptions. When the component is built and tested on the test bench, when its real behavior is finally observed. This trial and error approach works, but it has a limitation. Problems often emerge later in the process. As a result, development enters in an iterative loop: design, test, modification, new test. This leads to waste resources, longer development times, and greater uncertainty around dynamic behavior and optimization. What's often missing isn't simulation itself, because in many cases it's already there. What's missing is something more structural, a way to integrate simulation into the workflow so that it consistently supports design decisions, testing activities, and also development iterations, rather than remaining a standalone or occasional task. The approach we propose is to use the same virtual model across multiple contexts. Instead of creating separate models of each activity, we reuse the same object in design, in testing, in system-level simulation, and even toward the customer. This makes it possible to avoid losing information and to create continuity across the different phases. We've seen the problem and what's missing. Now let's look at how to build this workflow, following a very concrete practical path. We start from the engineering office, where we see how simulation supports both the development of new prototypes and redesign activities, leading all the way to system-level simulation. Then we move to the test bench, where the model is used to simulate experimental test results. Finally, we look at customer support, showing how simulation can be used to perform functional and performance checks. And finally, extending the model to the customer. That is, showing how models can be shared and used externally in different scenarios. So we follow the same common thread across all of these phases. To make this concept clearer, we'll use a guiding case study. We'll follow the VIS C0 S08 through this entire webinar. The same valve we modeled in the first session. We've chosen this simple valve for clarity, but the same approach applies to much more complex components as well. We look at it through different phases and, above all, at different levels of detail. These allow us to understand not just the individual tools, but how they are connected and work together. Let's take this valve an example. We can represent this valve in a simplified way, for instance, with a model calibrated using datasheet curves, or in detailed way, with a physics-based model that describes the internal behavior, as we did in the first webinar. These two levels are not alternatives, they are complementary. This means the same components can be used in different contexts while maintaining consistency between models. The point is not to choose one or the other, but to use the one that best fits the phase we are in. Within the collaboration with VIS, an ongoing project is modeling the entire valve catalog in both simplified and detailed versions, specifically to enable reuse across different contexts we will look at. If we look at the engineering office, the change is quite clear. Without integrated simulation, many issues only emerge during the testing phase. With simulation, we can anticipate them already during the design phase. This results in fewer iterations and greater control over the component's behavior. We look at three typical activities: prototyping, redesign, and integration into system. We begin with the prototyping activity and return to our guiding case. Here we used a detailed model of the C0 in which we can calibrate, for example, pressure losses. Through CFD simulations, we can evaluate the impact of internal geometry already in the design stage. This image shows the distributions of velocity and pressure. The latter in particular is useful to finding model calibration, especially for determining the discharge coefficients of orifices equivalent to the geometric flow paths of the component when installed in its cavity. An analysis of this type makes it possible to take design decisions with greater awareness. Now let's step outside our guiding case for a moment and look at a more advanced example. Here we have a different valve, the SVP0 S10, on which CFD simulations were carried out on the spool geometry for the 3 versus 2 flow direction. The goal is to minimize the flow forces that oppose valve opening and therefore require higher force from the electric actuator. By modifying the terminal part of the spool, we can see how the flow is progressively redirected toward a more radial direction. As a result, there is a gradual reduction of flow forces, which also depend on the angle at which the fluid exits. The results of these simulations are then incorporated into the lumped parameter model to calibrate this model in detail. In fact, force maps are generated as a function of valve, of stroke of valve and flow rate. This is a more complex example, but the underlying principle is exactly the same, using simulation to guide design decisions. We continue with the redesign activity and return to our guiding case. Here, the C0 model is calibrated using experimental data. Starting from test bench curves and with support from CFD, flow forces are calculated in detail. The results are then introduced into the model through a force table as a function of valve stroke and flow rate. In this way, it becomes possible to accurately simulate the effects of geometry modifications to the original design. As a result, the model is no longer just theoretical, but it becomes a representation of real behavior. A similar example on another valve is this one. The valve is R2P0M26, and this is its virtual model. Here, the dynamic model has been calibrated in both operating directions, using tables that correct the steady-state flow force formulation, in both cases as a function of flow rate and in the 1 versus 2 direction, also as a function of pressure setting. This is the resulting comparison between the simulated curve and the experimental curve, for example, at cracking pressure at 250 bar. This approach makes it possible to significantly reduce the gap between simulation and real behavior. Finally, we move on to system-level simulation. The same CVC0 valve can be integrated into a virtual model of a hydraulic circuit, for example, into the regeneration system that we have seen in the previous webinar. Depending on the objective, we can use either a simplified or detailed version of the valve, and this makes the component model scalable and reusable across different simulation contexts. As we move to the test bench, the next step is to model not only the valve itself, but also the experimental setup. The test bench becomes a detailed model in its own right, including real components, connections, and functionalities. This makes it possible to virtually reproduce the actual bench test for several purposes: predicting tests, reducing the number of physical tests required, and also improving test repeatability. Here you can see an interface that we developed for VIS Hydraulics that allows experimental tests to be virtually reproduced through a guided workflow. The key advantage is that simulations can be launched quickly, even without directly accessing Pneumodelica, by simply selecting the test bench, the valve under test, the configuration, and also the operating conditions. Here is an example, again based on our guiding case. So let's see this example of this interface. Here we can set our guiding valve, that is the CVC0. So this is the valve, this is the Pneumodelica model. Here we can choose what parameters we want to see in our interface, and also what variables we want to see at the end. And let's select also the test bed. This is one of the test bed that we have modeled in VIS Hydraulics. We can choose several preset configurations. For example, here we can select the configuration A, that is just input and inlet and outlet with pressure sensors and flow rate sensors. And we also can import this valve, and we have to select how we connect this test bed model to our test valve. So we connect the C1 to port 1 and C2 to port 2, and we can select the gas dimension of the connection, of this connection. So we can build this model and also launch the simulation. Here we have the complete interface. For example, we can change the spring in this valve. We can also set everything, and let's make an example looking at the pressure drop of this valve with this spring, for example. So we set the simulation, we launch the simulation. The simulation is running not in Pneumodelica, but in another window, so in background. As we wait that the simulation is finished, we can see here we have the complete setup. So the circuit, the hydraulic circuit, the model, the configuration. Also, we can change. We can activate different valves. We can change the piloting part of the circuit. We can also modify how the setting of these valves, and this is an example of this valve at this setting. So this is the example of the simulation with this spring. We can also load results. So we have the results here in Excel, this table, and also we have the plots here in the interface, and then we can add this configuration to the database so that we can recall this configuration later without doing again the process. Okay, let's go back to our presentation. Another use case that naturally emerges from this workflow is the customer decision support. By using simplified models of the circuit components, we can quickly perform functional and performance checks. This makes it possible to respond to customer requests in a faster and more reliable way. In this example, the valves are included as models that reproduce the catalog curves. This allows verification of the circuit's functionality, for example, by analyzing the cylinder stroke or of its energy performances, for example, with the hydraulic power. Simulation doesn't stop at the company boundary. It can be extended to the customer. By exchanging the necessary information, simulation can be run internally, and the results can be provided to the customer. Once the application parameters and operating conditions are known, the customer circuits can be virtually reproduced, for example, in this case, by integrating valve models into the simulation. The alternative path is to share the models directly with the customer. There are three scenarios for sharing models, depending on the client. The first case is if the client uses the same library, that is OpenModelica and our SmartFluidPower library. We can directly exchange models, hiding the internal information. The second case is if the client uses another LAMP parameter software. We can export the model as an FMU, for example, a protected black box. Third case, the client has no software. With OpenModelica, we can still provide a model usable with the open source tools. So, regardless of the context, there's always a way to make the model usable. Let's look at these three options, always apply to our case study. Let's start from the simplest case, using the same software environment, OpenModelica with SmartFluidPower library. In this case, the exchange is direct. The model is provided as a library component, but in encrypted form, that is .mol format. This means that the customer can see the icon and documentation, but not the internal mode. It is also possible to define which parameters are editable while preserving control over the know-how. From a practical standpoint, integration is immediate. The component is inserted into the model and connected in a plug-and-play manner. This is the simplest, most immediate, and most functional way to share a model. Let's quickly walk through our example. So, if we look at this library, this is an example library made for the client. Here we have our detailed model of the Cillo C0 with our code and an example testbed. This library can be exported in an encrypted way. So we make the encrypted file. And if we load this encrypted file in OpenModelica, again, OpenModelica, for example, in the software of our client. Okay, this is the library, and here you can see the same elements, the same models in the library, but all the informations are hidden. You can see just the icon and the documentation. That is, for example, this is the documentation of the valve, what are the springs, also the link to catalog here of the valve, and also testbed is encrypted. Encrypted means that you can see just documentation and the documentation and the icon. But also you can share some parameters that you want to show. Okay, let's see the second scenario, that is the second case, that is a different software. In this scenario, the model is exported as an FMU, meaning that it is provided as a protected black box. The FMI is a free standard for model exchange, supported by many different software tools. With the SmartFluidPower library and OpenModelica, the generated FMU is license-free and can therefore be used at no cost. The behavior is fully preserved, while the internal content remains inaccessible. Here as well, it is possible to decide which parameters and variables the user is allowed to modify or visualize. The FMU is then integrated into the customer's model through standard interfaces that convert the exchange variables into signals compatible across different environments. This is necessary because to enable co-simulation between different software tools, connections are based on dimensionless ports. This makes the setup slightly less direct, but also highly flexible and compatible with a wide range of environments. So let's have a quick look at our example. This is again the simple test bed that we are of our example. This is the model, the detailed model of the Cillo C0, and this is its conversion in FMU. What we have done is to remove the ports, the input and output port, and replace with these interface blocks that have split the variables that the ports are exchanging, that are pressure and flow rate. There is also the volume that is exchanging, but in this case we want to exchange just pressure and flow rate. So these interfaces are connected, and variables are split in dimensionless signals. Then we can export the FMU, and if we want to import the FMU in one of the software that are compatible with this FMU. Here we use again OpenModelica, but the same approach can be used in the other software of the list of the functional mockup interface. Here we can, in our test bed, we have to replace this model with our FMU. If we replace this one, we need some interfaces. That is, for example, this interface that have the same. Okay, we can connect these ports, the dimensionless ports, to the interface, and again use the interface for the outlet. Okay. Okay, so here we have reproduced the same circuit seen before, but just converting our ports in dimensionless port to communicate with our FMU, that is a general model that can be exchanged in softwares like this. Okay, let's see the last case. The example is if the customer does not have any simulation software. Even in this case, it is still possible to use the model. The FMU created with SmartFluidPower library, that is license-free, can be integrated into an open source environment. For example, OpenModelica, again, through the Modelica standard library, provides several open libraries, including the hydraulic one. The concept is the same. The FMU model communicates with the circuit through dimensionless ports, and the circuit, in turn, must include interface converters to adapt the connection ports. In this way, it is possible to build even simple system models and simulate the component's behavior. As a result, simulation remains accessible even without commercial tools. To sum up, what really changes? The model becomes a continuous element across departments. It is no longer an isolated activity, but a link between design, testing, and usage. This leads to greater continuity, fewer iterations, and higher efficiency, both at the product level and the process level. And this is the real shift in approach. At this point, I'll hand things back to Emiliano for a brief comment on the direct experience.
Yeah, as anticipated at the beginning, our main objective was to make the simulation an active design tool, not just a verification tool. So over the past year, we introduced a practice that has now become like a standard at VIS. For every new product, we develop the valve concept and its dynamic model in parallel. In the beginning, for sure, this requires additional effort and slight increased development time, but over time, virtuous circle emerge. So existing models became the foundation for new ones, and the development time has been progressively reduced. So the benefits are significant. On one end, we can reduce the number of design iterations and reach a functional solution earlier. So also limiting the amount of physical testing required. On the other hand, we gain a much deeper understanding of what actually happens inside the product. And also by comparing simulation results with the experimental one, we can analyze valve behavior in more detail and use this insight for daily problem solving, such as stability issues, dynamic response, or unexpected interaction between the components inside the valve. In some cases, also the simulation allows us to evaluate operating conditions that are difficult and practical to reproduce on a test bench. For example, very high pressure or high flow, and identify the potential critical in advance. We also use these models to support our customers, making a simulation not only an internal engineering tool, but a means of technical collaboration that tends to increase the shared know-how between VIS and our customer. And also, in some cases, these collaboration have results in the sharing of valve models as package, providing the customer with their ready-to-use simulation models that can be directly integrated into their development and system-level analysis. So we very happy to be part of this Open Modelica world, because it helps a lot in our design and our develop of product.
Okay, thank you, Emiliano. To conclude, just one important point. It's not necessary to introduce all of these at once. Typically, you start with a pilot case of interest, then a component or system model, and then after evaluating the functionality and potential approach, this approach can progressively extend it. This makes the introduction of simulation within a company much more gradual and manageable, even in organizations with well-established processes. Okay, thank you, everyone. If there are any questions, we can focus on this part now.
Okay, thank you, Giovanni and Emiliano, for sharing your knowledge and experience about simulation, and thank you all for attending this third webinar. You receive the slide, the recording, a dedicated follow-up page shortly. If you have any question, you can reach out to SmartFluidPower or via website or LinkedIn, or put it or submit it in our chat. We also like to invite you to complete the end of session questionnaire, which I've shared in the chat, and which you can also access via the QR code on the screen. In addition to giving us valuable feedback about we can improve our content and better support companies in integrating simulation into their processes, the questionnaire will give you access to the materials created during today's live session, the SmartFluidPower trial library, so you can try by yourself our tool, and a dedicated free technical consultation focused on your specific use case. Of course, even those who couldn't attend live and are watching this recording later will be able to fill out the questionnaire we send by email and receive all the materials we have. At this point, we wait for some questions, if any. No? Okay. In our next session on May 6, we'll dive deeper into performance and energy optimization of hydraulics components and system. Don't miss it, and thank you again, and enjoy the rest of your day, and hope to see you at our next webinar.